One of the major topics at this year's conference is segment routing. So what I'd like, and later on today, you're going to have 2 sessions dedicated to this topic, to segment routing. So what I'd like to do in my presentation is to kind of set up a stage for the discussion we're going to have later on today. And the way how I want to set up a stage for the later presentations is to look at segment routing from one particular point of view. I want us to look at segment routing from pragmatic point of view. What is the value proposition of segment routing? What does it bring to the table? Oops. Right. So there are a couple of questions we need to answer as we try to figure out what's the value proposition of segment routing. Does segment routing can solve problems that we cannot solve today with already available technologies? Perhaps segment routing can offer us compelling practical benefits over what could be done with already available technologies. And notice that in both of these questions, I emphasize the word practical because this presentation is not an academic discourse on the topic of segment routing. Well, so how are we going to answer these 2 questions? Let me suggest that the best way to answer these 2 questions is to actually look at segment routing use cases. And of course, for that, we just have to look at the internet draft that describes these 2 use cases. So let's start with the first use case, hub-by-hub LSPs. Now, in segment routing, there is a new terminology for this. It's called IGP-based MPLS tunneling. But it is actually hub-by-hub LSPs. The fact that you come up with a different name doesn't change its nature. So the way how hub-by-hub LSPs are supported with segment routing is by relying on either ISIS or OSPF as a label distribution protocol. Segment routing claims that supporting hub-by-hub LSP with segment routing brings 2 benefits. One is simple operation, and the second is excellent scaling. I'm going to put the first one, simple operation, aside for a moment. I'm going to return to this later on. Let's just focus on excellent scaling. Let's say, for the sake of argument, that indeed segment routing does offer excellent scaling for hub-by-hub LSPs. So what? Do we have problems with scaling today for hub-by-hub LSPs? Well, so let's see how we handle hub-by-hub LSPs today. Today, hub-by-hub LSPs are supported using LDP as a label distribution protocol. So the question you may ask is, do we have any scaling problems with LDP-based hub-by-hub LSPs? And if indeed we do, then the next question you should ask is whether these problems due to the protocol itself, are they intrinsic to the protocol, or do they have to do with just particular implementation choices? Well, to answer this question, we have to look at one particular aspect of LDP. Namely, we have to look at ordered versus independent label distribution control. So let's start with ordered control. There are 2 important parts about ordered control. A router may initiate advertisements of a label mapping to its neighbors under 2 conditions. One is when the router itself is the egress for the fact that it wants to advertise to its neighbors. And the second condition is when the router already received label mapping for that fact from the next hub. That is it. Under no other condition, router can initiate advertisement of a label mapping for a given fact. The consequence of it is that by default, The only thing that router advertises in LDP are label mappings for the loopback addresses of the routers. And so if you look at the total number of mappings that by default are carried in LDP with ordered label distribution control, the total number of mappings is equal exactly to the number of routers in your LDP network. So that's ordered control. Now let's shift our attention to independent control. In contrast to ordered label distribution control, with independent control, router can initiate advertisement of a label mapping for a given FAQ without being an egress for that FAQ and without waiting for receiving label mapping from the next hop of that FAQ. So the consequence of it is that by default, router advertises in LDP mappings for all the routes that the router has in its own IGP. What it means in terms of the total number of mappings being advertised is that it's equal to the number of routers, but there's also a multiplicative factor here, times the average number of interfaces. And on a modern core router, you may have between a few tens to a few hundreds interfaces. So now you can see the difference between the ordered control and independent control. With independent control, you may end up between 1 and 2 order of magnitude more mappings being carried in a label distribution protocol in LDP. Well, that clearly has a cost. It has a cost both in the control and in the data plane. So what can we learn from this? Well, we all know that in general, implementation choices do matter. And here's yet another example where they matter a lot. Because with LDP, implementation choices have very significant impact on the number of mappings that are carried by LDP. So if we do have LDP scalability issues, then these issues have nothing to do with the protocol. They have to do with a particular implementation choices made by some vendors. And therefore, if you want to fix these scalability problems, you just have to fix your implementation. Segment routing is not a solution to a broken implementation. And that brings me to a meta question. The question you may ask is, do we have today in our MPLS toolkit sufficient mechanisms to build a large-scale MPLS infrastructure that is based on hub-by-hub LSPs? And the answer, of course, is yes. It's known as seamless MPLS. It's based on existing and well-known protocols, LDP and BGP. Apparently, to the authors of seamless MPLS, this infrastructure could handle hundreds of thousands of nodes. And moreover, there is a claim by one of the authors that apparently we have production implementation in both vendors and providers of seamless MPLS. So all of this involves no segment routing at all. So the bottom line is we have existing mechanisms today in our MPLS toolkit that allows us to build a large-scale MPLS infrastructure with hub-by-hub LSPs. The next use case I want to talk about is fast reroute with segment routing. And I call this use case tale of a simple solution. And you'll see in a moment why. Well, this tale starts around 10 years ago. And actually, 10 years ago, it wasn't even chapter 1 of this book. It was kind of preface, where at MPLS World 2004 in Washington, D.C., there was a presentation on using loop-free alternate to provide local protection. It didn't get that much attention initially, but about 4 or 5 years ago, it got much more attention. And I guess at that point, the notion of being, quote, simple had been attached to LFA. So LFA acquired this label of being simple. It claimed to be one of the major benefits of LFA. Well, unfortunately, there was a fly in the ointment. And the fly is that you cannot get 100% coverage. And how much coverage you're going to get? Well, it really depends on a particular network topology. So one suggestion that was made by the LFA proponents is that, well, service providers should just redesign their network around LFA limitations. And once they redesign their network, they're going to get simple solution with 100% of coverage. Well, I personally think that this idea of redesigning network to address limitation of a particular technology is just a joke. Well, so what else can you do? Well, that brings us to the second chapter of the simple book. Now we have LFA, but we also add to this remote LFA. Remote LFA introduced the notion of targeted LDP, so you need targeted LDP. But not to worry. We're still in the realm of a simple solution, so it's still simple. Unfortunately, we still have this fly in the ointment. We can't get rid of it. We still cannot get 100% coverage. Granted that combination of LFA and remote LFA gives you more coverage than just LFA only, but still less than 100%. So what can you do? Well, you go into chapter 3. Well, in chapter 3, we have LFA, remote LFA, and now we add to this RSVPTE. Now, it is certainly true that combination of LFA, remote LFA, and RSVPTE does provide you with 100% coverage for both link and node protection. We have RSVPTE in this picture in chapter 3. But according to those who proposed the solution, it doesn't seem like a big deal. It was quoted as being, quote, icing on the cake. You don't need that many RSVP LSPs. It's fully automated. So the question you may ask, aren't we done? Look, the goal is accomplished. We have 100% coverage. What would be the business case of producing yet another iteration on a simple solution? How much additional profits service providers are going to gain from yet another iteration? After all, let's remember that, first of all, fast reroute isn't supposed to be used that often, because if, in fact, it's used very often, means that your routers or links failed very often, and in this case, you have other problems to worry about. And moreover, fast reroute is just a local protection mechanism that's supposed to be used for a very short period of time until global restoration kicks in. So aren't we done? You know, apparently not. Which brings us to chapter 4. Now we have fast reroute with segment routing. So we keep LFA as is. We also keep remote LFA, but instead of targeted LDP, we use ISIS or OSPF as a labeled distribution protocol. And we replace RSVPTE with ISIS or OSPF as a labeled distribution protocol. What's truly amazing, through all 4 chapters, the only thing which is constant is simplicity. It's still simple. Okay, aren't we done now? You know, still not. Because now we have chapter 5. Topology-independent fast reroute. Well, at this point, the only question I have is, maybe we should wait for chapter 6 to arrive. So what lessons can we learn from this? Well, the most important lesson from that tale of a simple solution from the simple book is that the word simple, simplicity, acquired new meaning and new use. New meaning, as I put on that slide. And new use, the word simple and simplicity, becomes nothing more but a marketing buzzword. Well, we went through 5 chapters of the simple solution. We started with LFA, then we moved to LFA plus remote LFA, then we moved to LFA plus remote LFA plus RSVPTE. From there, we went to LFA plus remote LFA plus segment routing. From there to topology-independent fast route. Well, maybe it's time to stop. Maybe it's time to step back and look at other alternatives. like using RSVPT to build bypasses and use that for fast reroute. So let's take a look at this alternative. Well, it gives you 100% coverage against link protection. So you do have here topology-independent fast reroute for link protection. It involves no LFA, no remote LFA, no targeted LDP, no segment routing. These bypass LSPs are not used for normal forwarding. They're only used when you need traffic protection. Total number of such bypasses is fairly small, so it imposes very low scalability requirements on RSVPTE. In the past, one of the arguments against this approach was that service providers have to manually provision all these bypasses. You'll see in a moment why this is no longer the case. And as an extra bonus, this technology allows you to provide fast reroute not just for unicast, but for multicast as well. As I said, in the past, one of the arguments against this approach was the need to manually provision these bypasses. Well, this is no longer the case. Here is an example of config from one of the router vendors that shows what does it take on a router to provision these bypasses. 2 lines. That is it. Now, you can say that so far I've been talking about using RSVPT LSP bypasses for link protection, and that is all true. But exactly the same approach could be used for node protection as well. Now let's take a look at another use case, traffic engineering with segment routing. I want to start with one particular model of operation for traffic engineering. Traffic engineering with SDN controller. And I picked up this term SDN controller because SDN seems to be really fashionable nowadays, so I can't escape it. But if you actually look at what this SDN controller does for the purpose of traffic engineering, actually it's glorified PCE, path computation element. All what it does, it performs path computation for explicitly routed tunnels, and then communicate this information to the ingresses of the tunnels. So as I said, SDN controller is just stateful PCE. That's how you should think about it. Now, if you want to have standard-based traffic engineering with SDN controller, then it's likely that this solution is going to require PCE communication protocol, PSAP. And that is actually irrespective whether you're going to use segment routing or RSVPTE for setting up explicitly routed tunnels. There are clearly several benefits that centralized path computation brings to the table. And yesterday, Dave Ward mentioned some of them. For example, with centralized path computation, you could get better network bandwidth utilization than with distributed one. But let's not ignore the fact that centralized path computation has its own, quote, things to consider. And one of them is scaling consideration. Because when this SDN controller has to reestablish a whole bunch of LSPs at about the same time, it could be quite a burden on both the controller as well as on a PCE communication protocol. Now, you could say that, well, if I want to scale my SDN controller, I'm going to have more than one stateful PCE. Well, that is all fine, but that brings its own issues to the table, such as synchronizing traffic engineering database and LSP database. And these are not the only issues. You may take a look at the internet draft that talks about unanswered questions in PCE architecture. And I think you shouldn't ignore it. What is important to keep in mind that both the benefits as well as, quote, things to consider apply irrespective of whether one uses segment routing or RSVPTE for setting up explicit tunnels. So the question you may ask, do we really have to have segment routing if we want to do traffic engineering with SDN controller? Of course not. You can do it today using RSVPTE. Now let's take a look at the different model of operation, where you're doing traffic engineering with distributed path computation. In this case, you don't have SDN controller. You don't have PCE in the picture anymore, because each router is responsible for path computation for the tunnels originated by the router. The algorithm used for path computation is known as constrained SPF, CSPF. And as we talk about constraints, it's very important to keep in mind that bandwidth is one of the key constraints. And to understand why, let's remember that the purpose of traffic engineering is to optimize networking resources. And of course, bandwidth is one of the key networking resources that has to be optimized. And that is precisely why bandwidth is one of the key constraints that CSPF has to take into account. So supporting traffic engineering with bandwidth constraint and distributed CSPF can be done today, and we do it today, using RSVPTE for establishing explicitly routed LSPs. The question you may ask is, can we do the same if instead of RSVPTE, we're going to use segment routing? Well, for this, you should just look at the segment routing use case draft. And as I put on that slide, we have to wait for a future version of this use case draft to describe research opportunity. And if and when that happens, then we have to wait for this research opportunity to get translated into something which actually could be implemented by engineers. And then we can probably have it. But until that happens, there is no support for this model of operation with segment routing. Now, you may say that so far I described two ends of a spectrum. One is fully centralized SDN controller, and one is fully distributed. But it doesn't have to be this way. It doesn't have to be all or nothing, because some of the LSPs could be placed using centralized path computation, SDN controller, and the rest of the LSPs could be placed using distributed CSPF. And in fact, if you think about it, that is pretty much what we've been doing for a long time using offline tools, where offline tool would be responsible for placing some of the biggest traffic flows, and the rest of the traffic will be placed using distributed CSPF. So with this model of operation, you may ask, can we support this model of operation if we use RSVPTE as the mechanism to establish explicitly routed tunnels? And the answer, of course, is yes, we can do it. We can do it today. Well, can we do the same if instead of RSVPTE, you're going to use segment routing? And the answer is no, for a very simple reason. Remember what I said in the previous slide about doing distributed path computation with CSPF and segment routing, and the fact that it's not supported by segment routing. Well, you can say, well, OK, maybe I cannot do everything with segment routing, but maybe I can do centralized path computation using segment routing. And for LSPs that are placed using distributed path computation, I will use RSVPTE. Can you do that? Well, unfortunately, no either, because there are quite a few open questions that have to be addressed. So such aspects of distributed path computation and inability to support this model of operation with segment routing is not the only limitation that segment routing has when it's applied to traffic engineering. There are other aspects of segment routing that makes it fairly problematic in the context of traffic engineering. And one of them is the issue of deep label stack. So let's take a look at that. Well, first of all, by its nature, segment routing may require an ingress of a tunnel to push as many labels on the stack as the number of hops in the tunnel itself. Now, if you want to use explicitly routed tunnels for the purpose of traffic engineering, it means that it may be very hard to impose the upper bound, to predict the upper bound on a number of hubs for explicitly routed tunnels. And the upper bound could clearly exceed the diameter of a network. And yet, in reality, we have real routers deployed in the network. And real routers have real limitations. So the question you may ask is, what are you going to do if you have explicitly routed tunnel that has more hubs than the number of labels that the router can push on a stack? Well, the first answer I heard is, just don't worry, it wouldn't happen. Well, I think it's kind of a very dismissive and somewhat arrogant answer. So what else? Well, another answer I heard, well, we picked up few service provider networks and we did some simulation analysis on the service provider networks. And this simulation analysis showed that for these service provider networks, we need no more than M labels, and deploy routers can clearly push that many labels. Well, that's really great news for these few service provider networks. But does it mean that this statement is going to be true for every service provider network? Probably not. Yet another answer I heard is, well, yeah, it could happen that the number of hubs, the number of labels you have to push at the ingress is greater than what could be handled by the router. And if that happens, we're going to use compression algorithm. This is all nice and dandy, but the problem with this answer is that compression by its nature is nothing more but an opportunistic idea. It doesn't give you guaranteed results. So to make the long story short, none of these three answers are prudent. None of these three answers represent good engineering practice. If service providers are serious about doing traffic engineering with segment routing, they better know the exact behavior of a system at the boundary condition. What's going to happen when the number of labels you have to push exceeds the limitation of the router. And that brings me to the next topic related to traffic engineering. As you've seen so far, using traffic engineering with segment routing has certain drawbacks. So you may ask, why would you even bother doing this? And that brings us to the question of state. It is certainly true that traffic engineering may require a fairly large number of explicitly routed tunnels. Given that, the question you may ask is, where would the state for these tunnels be maintained? Well, with segment routing, claim to fame is that the state is not in a router but in a packet. And in fact, I heard from the proponents of segment routing saying that we can do very large traffic engineering with segment routing where a transit router would need no more than a few hundred or a few thousand of entries. Well, I think the fact that you may need only a few hundred or a few thousand of entries is really great news for router vendors who plan to build core routers that cannot hold more than a few hundred or a few thousand of entries. For the rest of us who build core routers with much higher capacity, I'm not sure that is very useful information. And as I said, state in a packet is not exactly free lunch. It has its own set of problems. So with this in mind, let's take a look at the alternative. State in network, in a router. So if you use RSVPT, explicitly routed LSPs, then we clearly have state in the router. So the question you may ask is, what are the practical problems for maintaining state in a router? To make this discussion less abstract and more concrete, I picked up a particular data point, 100,000 LSPs. As you know, I work for a router vendor, and I think that this number actually is fairly conservative. And I think that in reality, router vendors should aim at higher numbers than that. But just to make this discussion more concrete, I picked up that number. So I think it's reasonable to assume that a modern core router has enough forwarding table memory to hold state for 100,000 LSPs. And likewise, I think that the modern core router has enough memory in its control plane to maintain RSVPTE state for 100,000 LSPs. And the question I have is whether this router has enough control plane resources to handle RSVPT message overhead for these many LSPs. And you may ask, why all of a sudden I am fixated on this issue of message overhead? You see in a moment why. To understand why I'm so much fixated on the message overhead of RSVPT, let's step back and look at the origin of RSVPTE. It's based on RSVP. And RSVP is known as, quote, soft state protocol. Now, the term soft state is a fairly ambiguous one. So for the sake of this discussion, I want to precisely define what it means. And what it means is that state maintenance in RSVP relies on the periodic refresh messages. Specifically, with RSVP, message refresh is the only way to recover from loss of messages. So let's keep that in mind. Now, if we focus now on RSVPTE, it's very important for us to keep in mind that the state we're talking about has direct impact on the forwarding state. So RSVPTE state controls forwarding state, controls labels. And therefore, in the context of RSVPTE, it's very essential, very important to achieve fast state synchronization. Well, but if all we have is periodic refreshes, then the only thing for state synchronization is periodic refresh. So now let's go back to the question I asked in the previous slide about why am I so much preoccupied with the message overhead. Well, even if you look at the default refresh interval, which is 30 seconds, and if you think how many messages you'll need to support 100,000 LSPs in transit, you'll realize that a router will need to handle well over 10,000 RSVPT messages per second. This is not exactly a small number. But you can say, well, 30 seconds is really way too long interval. I want to have faster state synchronization. So maybe I should shorten my refresh interval. Well, unfortunately, you may accomplish exactly the opposite. And that is, by making refresh interval shorter, you actually can make state synchronization longer for a very simple reason. Because you'll create nothing more but more control traffic. And more control traffic on the receiver could cause congestion on the receiver, which means that messages will be lost. And the receiver in vanilla RSVP has no way to apply back pressure to the sender. So to make the long story short, the reason why I'm so much fixated on the control plane message overhead is because with RSVPTE, on one hand, it's very essential to achieve fast state synchronization. And yet without refresh reduction, the only mechanism that RSVPTE has is the periodic refreshes. So the problem is not periodic refreshes per se. The problem is that these periodic refreshes are used for state synchronization. And just to add insult to injury, we also don't have any mechanism for the receiver to apply back pressure to the sender. So now enters RSVPTE with refresh reduction. What it brings to the table is a mechanism for reliable message delivery. And as a result, you can completely unbundle periodic refreshes from fast state synchronization. You don't need refreshes for fast state synchronization. And therefore, you could reduce the rate of refreshes to arbitrary low value. In addition to that, RFC 2961 that defines refresh reduction also provides a mechanism by which a receiver could indicate to the sender that the receiver is busy, and for the sender to react to that. Moreover, 2961 also has two other mechanisms that further allow us to improve control plane scaling, RSVPT control plane scaling. So in the end, RSVPTE with refresh reduction clearly has sufficient protocol machinery to make it possible for a modern router to handle RSVPTE message overhead for 100,000 LSPs. So combined with the observation I made early on about forwarding plane state and control plane memory, you should be able to say, well, modern core routers should be able to handle 100,000 transit LSPs. And yet, if you look at what's available in the market, I don't think you'll find that many routers that can actually handle that. So what's missing? What's missing is a good scalable implementation of RSVPT with refresh reduction. So going back to the issue of state in the router, state in the router by itself is not really a problem for doing large-scale traffic engineering with RSVPT. What is the problem is the message overhead required to maintain that state. But the message overhead is not the problem of a protocol itself. It's the problem of deficient implementations. And so this problem has to be addressed by fixing implementations, not by replacing RSVPT with segment routing. Well, the next use case I want to talk about is multicast. I think this slide is self-explanatory. There is nothing I can add or subtract to it. And that brings me to the last slide. It's very important for us to be able to distinguish between problems or shortcomings of LDP or RSVPT as protocols, problems that are intrinsic to these protocols, versus deficiencies or shortcomings due to the implementations of these protocols. And the reason why it's important to be able to distinguish between these two cases is because it'll tell us how to address these shortcomings. If the shortcomings are due to the implementations of LDP or RSVPT, then addressing the shortcomings should be done by fixing implementations, not by replacing these protocols with segment routing. In a previous presentation, Andy Mullis talked about standards and said that, look, we don't need as many standards as possible. So the attitude where I don't like or I don't want standard technology X is not really a good justification for producing yet another standard that has very similar or the same functionality as X. So going back to the questions I posed at the beginning of my presentation, does segment routing allow us to solve problems that we cannot solve with currently available technologies? Does segment routing provide compelling benefits over the solutions that could be accomplished with the existing standards? Or do we have a case where segment routing is just a solution looking for a problem? I think these are the questions that each of you have to answer on your own as you listen to segment routing. And that is the end. Thank you.
Thank you very much.